And we'll go ahead and dive in. So welcome, great to see everybody. Today we're going to be talking about a little bit of review of mathematics and some other stuff related to just getting our project set up with the compilation process and kind of debugging some of those issues if we need to. But where I wanted to start here is, just kind of looking around. And I find these sorts of opportunities on Twitter and LinkedIn on actual game engine programmer jobs. So, it's something to keep in mind. And I think today, the lecture, as far as the contents go, and really this course's goal is to prepare you for a game industry job. So this was actually from a year ago, so it's a little bit old, but it was from a famous programmer, Jonathan Blow, who's sort of famous in the game programming community. To stumble upon these tweets every once in a while, or LinkedIn, or those types of things. So I thought this was just kind of fun and timely, although this was from about 2 years ago here, but you never know where these opportunities will come up. But with that said, I want to go ahead and get us started with some of our logistics here. So another assignment should be pushed to your repository, so you can do a git pull at any point. I've pushed that as far about 20 or so minutes ago. And of course, your assignment 3 is out at this point. So let me just go ahead and pause here for a moment and see if anybody in Vancouver has any questions regarding assignment 3 that you want to ask.
I have a question for assignment 3 for the resource manager. There's some function called startup. I feel a little bit confused about this function. I don't know what should be inside this startup. It's like, well, everything for singleton, I can just use the get instance to get an instance.
Yeah, and I think it's probably true. Let me see here. Let me open up the actual assignment. It's probably true for assignment 3 that there's not much work to actually be done in the startup function here. So our constructor actually doesn't really do much, and the reality is for your resource manager, if you're using something like a map in this data structure, that's got its own sort of setup and these types of things. So I don't think there's really any work to be done in startup here. Now in shutdown, you might have something, for instance, if you're keeping track of all of your SDL surfaces to iterate through and remove them. That would be the only work to do in shutdown. So that's sort of the goal. Does that make sense?
Yes.
Yep. So we're doing pretty much exactly, again, as you mentioned, all the work that you'd be doing in your destructor and constructor, but you've got the ability to restart this process. Other questions about the previous homework or anything else going on with the course?
So just wondering, do we want to keep the surface or the texture in the resource manager?
For this assignment, the intent was to keep the surface. Now, in reality, if you want for your resource manager, if you want to configure this such that it takes your, or basically has a map for the surfaces and the textures, that's fine. But at the least, you need to store the surface. You should have a map for the file name, for the surface, and then the actual SDL surface that only gets loaded one time.
That means we can load the texture multiple times?
That's true. Yeah, we are going to create the texture multiple times in that case. So if you want to do both, that's fine. That's actually optimal. We would have to, the only thing that we have to think about with the texture, and this is sort of an open question, is how do we want to look up that texture? And maybe let me get my drawing pad ready here so I can draw the question here. Let's see here. To define the grid. Oops, I gotta load this up one more time. What do folks think about that? Meaning, for the SDL surface, right? Whenever we've loaded that, we have some surface here. We call the SDL load BMP function, and then we have a unique string here. So this is our sort of key, and then this is our value. For SDL texture, right, we have some texture, and then I forget exactly what the function is, but something like SDL, create texture from surface, I think it is. And then you pass in the surface. So in this case, what's our key and what's our value going to be?
I think the value is the texture. The key is a path.
The name, the path. Sorry, the file name.
Or the surface itself.
Okay. Yeah. So the key itself could be, and it's something for you to think about. It could be another SDL surface where you want to check and say, hey, have I made another texture from this surface before? Or you could also use the file name. I suppose that would be fine if that's sort of the intent of just as long as it's uniquely identified. The one corner case I can think of, and we haven't really talked about, is with a transparent texture, right? So when you load an image, something like this, a smiley face, you typically don't want all the stuff, all the extra pixels here. But maybe sometimes you do. So, that could mean you'd have two different surfaces, one for the sort of transparent, smiley face with nothing around it, and then another surface for this actual smiley face with all the pixels around it. So that's the idea for why you might want to think about that just a tiny bit. In many cases, it might just not matter, and it's fine to use the file name, or as folks said, just pass in a surface as the key. And then you'd sort of do the same lookup and say, well, if I don't have that actual surface, then I need to load it first, store that in my resource manager, and proceed forward. Yeah, so great questions. Other questions? Yeah.
I have a question. I know the surfaces live on the memory, but my question is, where is the texture live? Is it live in the GPU or still live in memory?
Yep. So texture is going to be in GPU. So that's where it's stored, and that's the idea. When you're actually getting this pointer here from the texture, I haven't looked in SDL recently, so I'd have to look again at the source code, but at least the way it's done in OpenGL and other graphics APIs, right? This pointer that you're getting here to this texture is some location and memory in the GPU that it's using to say, hey, this is where in the actual graphics card memory this texture is, sort of a handle to that data, if that makes sense. OpenGL, or excuse me, SDL just allows us to use this, though. It's a little bit convenient for us. Yeah, other questions? These are great questions about the resource manager. Because eventually we're going to have a bunch of different manager classes managing our resources. So as you folks are thinking about this, right, you'll have at least a manager for maybe surfaces. Maybe you'll divide up and have another manager for your textures, and then eventually our sprites will probably want to be managed, and we'll call those entities and have a manager for that at the least. And then any other sort of components or resources that we load, things like sounds or media files, etc. We'll want to look up from resource managers. So other questions about assignment 3? I think there were a few other nice posts on Piazza about using static and some of these things that folks can look at. And there might be a few other posts I'll catch up on after class otherwise. Okay, so with that said, let me go ahead and I'll remove this for now. And I'll be in the recording if you need it. We'll keep our drawing board here. And just looking at our logistics going forward, again, we are in module 4, and we're going to talk a little bit about our project structure and then a little bit of a math review. So depending on what math classes you've taken and when the last time you took one, or if you've taken linear algebra, just get a little bit of review on some of the sort of essential math tools, and that'll prepare us for our homework, which will be building a little math library. So that's our goal going forward here. Let's go ahead and proceed. So again, last time we were talking about these things that you're asking questions about, our resource manager to deal with assets and resources and games. We refer to as the asset pipeline, basically just the idea of, how do I get bitmap images or sound files or whatever data, through some tool or our managers and eventually into a format that our game engine understands. So, what this really requires us to understand, at least for now, is basic input-output for our files. So whether those are the C functions or what's available in SDL, functions like SDL load bitmap, that makes things relatively easy for us. And there will be a few different optimizations we can apply. And I'll kind of look at kind of shuffling some stuff around towards the end of the course, meaning we might want to actually compress all of these files. We might want to, in our resource manager, just, for instance, load a zip at once, rather than having to individually load all of these files, and then look up things as needed as you sort of query for them. So those will be a few things that we'll want to think about, as well as for file I/O. And again, depending on what courses folks have taken, if you've done some web development or other courses where you use concurrency, we might want to actually look at some asynchronous file I/O as well. In C++, we can do neat things with std async, so a couple other things that we can build on. But all those ideas and things are captured in our resource manager, which we're usually going to be using some sort of singleton pattern, because it's usually pretty convenient for us to have a global place to ask for a resource. Now, eventually, we're going to kind of think about how we might want to refactor this singleton into some other design pattern as well to make it, again, convenient for us. So that's the idea there. And then as well as with the resource manager, we talked a little bit about containers. So at the least in this course, you'll want to be familiar with standard vector, standard unordered map, and standard map. Those are likely going to be your go-to data structures built into C++ that we'll want to be using. I think these are going to be, I want to say these are the only 3, although there could be some others we might want to list, for instance. Those are sort of the most common ones that we use. And then finally, we got to this, initialization and shutdown pattern, which again is a little bit weird. You can kind of see a screenshot on the top left here of the startup and shutdown. But again, it's just a way to give us control over our functions. We're basically manually writing our constructor or destructor as needed, so that we can start up or shut down systems or reset them or whatever functionality that we otherwise would need in our engine. Because again, we want control. So that was last time. For today, we're going to continue looking at some core systems and parts of that in our engine. So I'll start off again just with some C++ concepts here, but ultimately we're going to be building a little math library. I should state that this isn't going to be everything that you might need, depending on the type of game and game engine you choose to build at the end of the course. But it'll be a good start for us, just to refresh on math, and then we'll get to applying it in some game projects here in a little bit. So while we're building this little math library, we'll refresh your algebra skills. And then towards the end of the lecture, and I'll kind of pace it towards time, it's actually an optional part of your next homework. It's using what are called single instruction multiple data, which is a way to get parallelism on your CPU in your math library. So this is a pretty neat topic, I would say, and just understanding what your modern hardware is capable of doing. By modern, I mean since like 1995. These have just been things that have been around a long time, but we just don't use them for math because, folks don't know about it. So that's sort of the idea. So, we're going to focus on this math library, unit testing, not so much memory allocation, but working with memory, I should say here, and hopefully learn a few tricks along the way. So with that said, let me kind of go into a little bit of C++ concepts, just a few slides on this, just to make sure everyone's concrete. I've seen some questions, regarding this topic just on compilation, because the idea is today that we're building a little library that we want to hook into our code. So we really need to understand how to compile our software. So now for those of you who watched that 54-minute video or whatever, you should be in pretty good shape. But again, this is just illustrating this process of, compiling separate C++ files here. So our source code coming through a compiler and generating some intermediate file that ultimately gets glued together by a tool called the linker. Now the linker has been the tool behind the scenes that's brought in our library SDL. So again, we didn't write the SDL code at all. Someone else wrote it, compiled it, and then we link or glue together that code. So just want to sort of have that in mind with how that's working here. So I think it is useful, folks, to see again our build file, because we'll be adding stuff. Again, I was quite pleased that a lot of folks sort of explored the SDL TTF library. That's great. And then kind of figured out where, in the libraries to, link in the framework or the TTF file. So here I've just got, showing on Mac, so you can look at, the sort of middle instructions. Darwin is what Mac is identified as. And just going through the compilation again. Now every time you run the Python build.py file, it'll show you what's compiling. But again, it's worth understanding, the first set of arguments is, well, the compiler, Clang++ or G++, the standard of the language that you're using. So C++ at least 17 or 20 for most of this class. And then the -D is a special define flag. And I've sort of defined this as Mac, Windows, or Linux. And I'll actually show you in code where that's useful or why that's there. And this is sort of my cheat for now for supporting this class for Windows, Linux, and Mac development. But if you go into any of the sort of SDL programs here, and actually let me go back to the header file here. So anywhere where you're doing SDL stuff, you might have noticed something like this here. Now, since we've defined Mac, well, we haven't defined Linux or Windows, so we use this path for including your SDL. That's, just Mac had to be a little bit different here. But that's sort of a common way of handling what I would say is called conditional compilation. So based off of, the arguments that we pass into our compiler, we use this code to compile, or otherwise we use this code. Okay, does that make sense to folks? Questions about that? All right, awesome. Just want to kind of reduce the magic in case folks were wondering about that. But that's the idea of why that flag exists and why you might see it in other software projects. So the next part is in this compilation is -O, and then whatever the executable name is. So usually I've named them things like lab or prog or assignment or something like that. That's how you're, of course, running the file. Windows folks are going to have lab.exe or something like that that ultimately gets generated. And then the include directories. So again, this is where we've been including SDL2. Again, this is showing on Mac here. So where I am underlining here where SDL2 lives. You might have additional math libraries. This is just an example showing some math libraries. And you might have additional include libraries. So when I do -I and then the /include is important because, again, that's indicating a relative directory. So again, I had a couple of questions on this in office hours that we were debugging. That just means that from my root directory, wherever I'm compiling this, I'm looking in /include. So that means, look in this actual folder. And then it will know to look for these things here. In this case, for today, tinymath.hpp. So then when you're actually using it in your code, let's go ahead and see where we use it. You can actually just include on this path here. And in reality, it's looking in /include tinymath.hpp. Okay. So that's the idea there. And that's how your code knows where to find SDL, right? It knows to look in library, frameworks, SDL2 frameworks, and then the header files. And then if you look in this location for our Mac folks, you should find SDL.h here. Okay. So then the next part is just compiling all the source files. If all of your .cpp files are in the same source directory, you can just use a wildcard here, star.cpp, and that'll compile them all. So no problem there. And then finally, linking in the libraries. So again, this is where if you have, for instance, the sdl.c or any other C++ files from libraries that have been already compiled for you, that you're linking in, this is where you're linking them in. So -framework SDL2. And if you actually look for this file, I have to remember on Mac, but it'll usually be something like lib sdl2.dylib or something like that. So usually you omit the extensions, but it'll look something like that here. That's just the sort of convention. And Mac's a little bit different. It's got these frameworks. If you look at the Linux or the Windows ones, like on line 20 here, you'll notice it's just -L, capital SDL2, and that's it. Okay. I know that's a little bit small for our folks watching the classroom, so here it is bigger. Here, that's what I'm highlighting for our Linux folks. So that's the idea. All right. So let me pause there for a moment. Do folks have any, questions about this process or what's been going on in build.py?
I have a question for the Linux. What is LDL? Is like link for the DL?
Yeah, let's see if I can actually show you on Linux. And Mac and Windows have an equivalent. Let's see. Actually, I'll just look for a function here. Well, let me show you two cool things that you may not know. One is on the terminal, if you just look for any C-based function, you can get to a help page. For C++, there's a program called CPP-man that you can look for. So if you type something like vector, then you'll get some help pages. That's kind of neat. But as far as the, what's the, let me make this, as big as possible so you can see the link DL thing. Well, DL itself stands for Dynamic Library. And what that is, so I'll actually just show you a function here that exists, is we have actual C functions where we load libraries. So SDL is actually loaded when your program starts running. Okay. So, here's our application, and you're going to get ready to do something in SDL. I don't know, draw a triangle. But before that happens, somewhere in your source code, right? So here's the, SDL. Here, let me write this a little bit bigger here. SDL init function. But before you can even call an SDL init, there's actually going to be a function here somewhere. I'll write it open. I'll DL open, and it's going to look for that library, SDL lib .so or whatever extension it needs. And that's finding the actual file here, SDL that shared object file. And again, usually it has lib in front of it, SDL2. and it loads up the code right before your program starts running. So the DL and why we're including that in our command line, this link DL, is so we have that capability to load libraries at runtime, if that makes sense. Yep. And we're actually going to play around with this a little bit, because when we think about our game engines, you know, or especially for folks who have used Unity that are loading in scripts, for instance, that's kind of the same idea. It's actually the same idea whenever you use a command, just to simplify this a little bit, like fopen, right, to open a file, you know, some file.txt. It's doing the exact same thing, except the type of file that we're actually looking for with DL open here, DL open, just happens to be, you know, a piece of binary code that contains a bunch of functions that we want to use. So that's sort of the idea. If folks want to follow up, one of the next videos I'm going to film is actually going to be talking about DL open and how to use some of this stuff. If folks send me a reminder, I'll kind of push it up the queue. I probably do it in like 2 or 3 weeks. It's not super important, but I think it is interesting. Other questions from folks? So, well, if you have any questions, you know, feel free to look on Piazza or, you know, watch that 54-minute video. That's again going to be part of our part 0 of this next homework, sort of the warm up, really just understanding this process. And the reason I'm, you know, having folks really understand this process is from a game engine programmer perspective. You kind of have to know how all the stuff works and how libraries are loaded, because that's essentially what your engine's going to be doing. So, you know, compiling software, compiling our engine is an important part of that. But with that, you know, thinking about this process, you know, we're going to build a math library, and we have a decision to make here, because we could compile our code and load it as a library, you know, sort of like SDL, or maybe we just say, hey, we're going to incorporate this in our code with a, you know, header file and then an implementation file, and use it that way, right? Because we have the code anyway. Or maybe we just create a header only file. And what I'd like you to think about, sort of a open question, is, you know, which approach should we go with? Now, granted, I'm forcing you to use one already, but which approach do you think we should go with here?
The first one?
First one? Yeah. Why would we think the first one? And there's no right answer, and you know, I'm already gonna. They all have their trade-offs, I should say.
I guess, like, if we use a safe one, as the first one, then we don't have to compile it again.
Yeah, that's true. Once it's compiled, right, we just link it in every time we rebuild, and that's going to save us some time. That's going to be pretty important, especially as our engines would grow larger, not recompiling the whole library. Maybe, you know, when we link in code, you know, we can leverage it and, you know, our game engine, all of our games, that would probably have a library. That's probably a good idea. What do other folks think? Well, let me give you a little bit of insight, because it might be a tricky question, because there are really trade-offs between all these approaches. So you have a pro and con with each. You know, with this first option, we could compile our code as a separate library, you know, a shared object file or a DLL. And that's especially useful, as mentioned, you know, for distributing to multiple projects. And we don't need to share the code with anybody, you know. So that's kind of nice. And as mentioned, we don't have to just keep recompiling it. On the con side, though, you know, we do pay a little bit of penalty with dynamic linking, but we could actually statically link this. So that's okay, right? So we could probably get around that. Now with the second and third option, we could just have a C++ file and then a header file, and compile it into our code. And, that could be very good for optimizations. We could just sort of control that pipeline here. The con here, I said, well, kind of goes to the third option. Let's just get rid of the C++ file. Why not just implement it all in the header file? Now this is sort of breaking what I showed you in the quick start video, but this class is kind of breaking a lot of the rules. That's kind of the point with some of the trade-offs we make in game development. With a header only library, probably simpler to implement, right? We're just going to put everything in the header library. Now the con to that is if I have a bunch of implementation in my header, if I do it in a sort of suboptimal way, that could slow down the compilation process, because every time I make a change now in my source code in my header file, well, any file that includes that header automatically has to be recompiled whenever we rebuild. And that'll come more into play if we have a build system. So these are just some of the trade-offs I want you to sort of have in mind as we're building these things. The reality is I'm going to default us into the header-only option because it's the simplest. And I think until our project starts getting larger, then we'll want to think about some of these other options. So just going, and showing you in the code, what does header-only mean? Well, whenever we want to use our math functions, we just include our library as such. And you'll notice there's no tiny math CPP file here. There's only in our include directory tinymath.hpp. Okay, and you'll see here we have a struct, and we have all the implementation code mixed in here. Okay, so again, it's breaking a lot of the rules. There is one or two reasons to do this. Again, simplicity is one, but also, it's helpful when we want to use some of these functions like inline here, and I'll talk about that in a little bit. But anyways, that's what I'm going to default this into. It's easy for us to get started. We won't have to worry for a little bit until our projects get a tiny bit bigger. All right, does that make sense to folks? Right. All right. So with that in mind, with what we're building and compiling and building our software, we're going to have to understand some mathematics in games here. The good news is I can almost guarantee that everybody's seen most of these topics somewhere in their schooling curriculum, right? Certainly algebra, geometry, and trigonometry. I can be assured that pretty much everyone's seen these things. Some amount of statistics, you've probably had some amount of linear algebra, whether in these courses or a separate course, and probably some amount of calculus as well. Again, even if you don't have a math background, you've probably done some or used some tools that depend on calculus. So, our goal is going to be to implement some of these functions, or rather data structures, that allow us to use trigonometry, linear algebra to solve game problems. Okay. So that's our goal here today. So I'm building this math library. And the key components of a math library, we need at least two data structures. Usually that's going to be something like what we'll call a vector 2D and a matrix data structure, which I'll call matrix 3 by 3, indicating 3 rows and 3 columns. So that's sort of our goal. And of course, we need to make sure that the mathematics is correct. So that's one of the challenges, because everything that we do in our games builds off these libraries. We want these libraries to be relatively easy to use as well. So that means little things like, for instance, and let me just show an example. If I have a little grid here and I have a point here at some location and another point here at some location, if I wanted to subtract these points here, point A and point B, it's kind of nice if in my interface I can just do A minus B, rather than doing A subtract B or whatever. So again, that's just on the usability. And we call this overloading. So depending on what languages you've used, you may or may not have the ability to overload operators like minus and plus and so on. Okay, so that's the idea. And then ultimately, and this is where the sort of bonus part of this lecture goes, is you want these math operations to be fast, as fast as possible, and lightweight in terms of memory. So that sort of means some sort of measurement should be done. So that's what we're going to be working on here. So again, why build a library at this point? Well, it's sort of better than one just sort of doing these calculations ad hoc, meaning as you need them. It's useful to have some functions. Typically, it's nice to build a library, again, thinking from an engine standpoint, to control the intellectual property, having exactly what you need for your game. And if you have the code, it's something that you can test, with your own confidence and debug, right? Again, to have the code. There's many libraries out there, but I think it's important to know how to build one. And use it and grow it and to think about some of these things about how you actually want to use it, what the interface is. All right, so getting on with some game math here, I'll talk about a few topics. So starting with numbers. So the very first thing that we want to know about is these terms you'll hear, like a scalar. Which is just a way to say, sum, singular value, integer, float, double, etc. So here's an example creating a float. The actual proper way to create a float, and you'll usually see me do this in code if I'm being good, is to go float x and then 1.0 f at the end to indicate explicitly that it's a float. 1.0 is a double, so there's a conversion going on there, so we kind of avoid that. But that's the idea here. A single number is a scalar. And typically, again, you'll see me use floats for mostly in this course anytime we need a decimal number, because that's precise enough in a game. You might use doubles or something for more precision in a graphics application, but a float's good enough for this course and most games, so that's what we use. All right, so once we have a number, we might want some combination of numbers. So thinking about the coordinate system that we're working in is important. So we can start with a sort of a typical, I think what comes to mind for most folks, a Cartesian coordinate system. Again, just plotting an x, y, and a z if we're working in 3 dimensions. Today, most of the examples will be 2D, but some 3D examples. Right, in 2D coordinates, you have 2 dimensions, 3D, you have 3. I can kind of just show here. Again, here's a 2D Cartesian coordinate system. And then 3D, of course, you have a z-axis here. So x, y, and z. And of course, these can be flipped or in sort of any orientation, but here's probably the most common orientations where we see x going horizontally, y up and down, and so on. And just again, important just for notation, right? 0, 0 is the origin. So just, that's where we're usually working from. Now, Cartesian coordinate systems are great. I'm sure you're pretty familiar with these, but there's other types of coordinate systems depending on what problem you're trying to solve. So again, probably something you did at some point in your school, working in polar coordinates or cylindrical coordinates in 3D. But this idea that sometimes it's nice to be able to think about the angle on the rotation, and again, usually thinking from the origin here. So on occasion, you'll want to be able to convert between Cartesian and polar coordinates. This tends to work a little bit better if you're trying to, orbit some object around the other to think about the angle that it's moving around, versus trying to figure out the exact x and y position to move something. So that's sort of the idea there, that we'll, want to be able to convert back and forth. All right. So with that in mind, let's talk about one of our key data structures that I mentioned, vector. And what is a vector? Well, the definition here, it's a quantity that has a magnitude and a direction. So Here's an example here on the grid on the right image. This is a vector that we would call 3, 3. So the tail or the starting point is at 0, 0. And then it extends out 3 units on the x and 3 units on the y-axis, indicated by 3 and 3 respectively. So that's the idea, and then we usually visualize the tail and the head with a arrow where the head is, again, showing us the direction that the vector is moving. The magnitude is the length. I'll show you how to calculate that in a moment, but that's the idea of what a vector is. So it's not a 0.33, but it is something with a length and a direction, okay? So a note here, and I guess this is a note for Unity folks, and I'll get to this when we actually create the data structure. You know, if you've done some game programming, you oftentimes will just use a vector 3 or a vector 2D or something like that to represent position or sometimes a velocity, because, you know, if I go back here, the confusing thing is this sort of looks like an X and a Y. So we'll need some sort of way to differentiate, or I would say it's useful if we can differentiate between what is a point and a vector in our actual data structure. Because, you know, we could, and let me be just very explicit about this in our code. All right, let's create some project here. I could have a struct, you know, point2D that would have an X and a Y. And a struct, you know, vector 2D that could have a float with an X and a Y, right? And these are basically equivalent here. So usually we end up just defining one of these, and then we, you know, need a way to determine, well, is this a position in space or is it something with a magnitude and a direction? And sometimes, folks, just to give you something to think about here, do actually define this as something with a magnitude and the direction as such. So it just depends on the definition. But most commonly, you know, here's a vector 2D. Here's the, you know, minimum example. Okay. Okay, but yeah, just want to keep that in mind that, you know, a position is different than a vector. Okay. So, you know, with that in mind, I want to actually show you the trick that I'm going to use that I think will be useful. And I'll show you in your code here, your sample code. But the reason I'm also picking out this example is it's a little bit interesting from a programming perspective. I wanted to throw something at you that, you know, I think is useful just to understand from a coding perspective. So let me bring up our vec2d here, and I'm actually just going to copy a part of it. I think it's a little bit easier to see on a black background for you folks here. All right, and I'm going to have to make it a little bit smaller here. All right. So again, let's see. Let me actually get rid of the comments and make it bigger for you folks in Vancouver here. Let's see. Just one moment. Let's delete all this. Okay. And oops. All right, now I can make this nice and large here. It's a little better. Extremely big. Okay. Okay, let's just look at this, you know, part of our vec2d here. So what I've got here, again, here's the name of our data structure here, vec2d. And then I've got, you know, this chunk here. These are all the member variables. So I'm just by maybe a show of hand, how many folks have seen union before in code? Okay, one person. Yeah, maybe you've done some C programming. Does anybody know what a union does for one person? Do you want to try to explain it?
So you can interpret, I don't know if that's the right word, but you can interpret the struct in different ways.
So the underlying data is the same, but you can interpret as shown here. You can interpret either as array or 3 different floats.
Yeah, that's perfect. So again, just to restate that, what a union is it's one collection of data. So let me remove that out of the way. So if I have a union of floats here, let's say data 2, or if I have, actually, let me simplify this even more. Let's just say I have float f here and int I. A union is not a class and it's not a struct. Basically, it takes one form or the other. Okay, so I can use this union.f, and I have to give it a name. So some union. So I could do some union.f equals 3.14, something like that. But if I access it as some union.I, this might be 3, for example. Even though I haven't set I in this particular instance. And in fact, float's a little bit wonky, but I think you'll get the point here. Right, the underlying data stores 3.14, but if I access this as an integer, so just one of these fields, then I take whatever my data is, which happens to be 3.14, and then I get that data out here. Okay, it actually works a little bit better in the other direction here, where if I say some union.I equals 3, and then I say printf, or since we're on C++ here, union.f, this would actually print out 3 here as well. Okay, because the underlying data, the only thing that's in the 4 bytes here, and it's important to sort of know the size here. So this is 4 bytes, 4 bytes, and the union takes on, or the union size is the largest data type. Okay, so again, even though I have 2 member variables here, I'm only using 4 bytes of data. Okay, it's just sometimes I want to interpret it as a float, sometimes I want to interpret it as a integer, whatever that happens to be in that 4 bytes of data. Okay, does that make sense to folks? Any questions about that? All right. So let me get rid of this and bring our vec2, because that's sort of the point here that, well, for our vec2d, we know we want at least an x and a y, but sometimes it's convenient to be able to pass around an array. Okay, so and in order to have that option of either doing x, y, and w, or accessing the array here, basically I build in a struct here, which is going to be 12 bytes of data, or I can use this float of, well, 3 floats, which is also 12 bytes. Okay, so what that means is, and I need to make this just a tiny bit smaller here. There we are. I'll put it in a comment. Data at 0 is equivalent to x. Okay. Data at 1 is equivalent to y, and data at 2 is equivalent to w. Okay, does that make sense to folks? So, whether I choose to access my vector with data 0 or with .x, it doesn't matter. It's still working on the same 12 bytes, where this is the first 4 bytes, next 4 bytes, etc. Last 4 bytes. Okay, does that make sense to folks? Oftentimes we have to think about things in terms of bytes or their data size, and a union's a really compact way sometimes to represent data. And it's sometimes a tool that can make our code more expressive. So again, with this vec2d, I can either pass around this data as an array or just access individually, the x, y, or the w components. Okay. Now, so any questions about that union and why I've chosen to represent it in this way?
I have a question. I'm a bit confused why use union on this struct.
Yeah, so let me so union here. So I'm declaring, this union, it's within this vec2d here. Okay, so this is only really one, the equivalent here. I could just would be for me to just say x, y, and w, right? And I could just end my struct here, and that would be fine. Or I could equivalently just use float data 3, okay? But I want the ability to say vec2d, my vec or something, say my vec dot x equals 7, or I want the ability to have a function and say void foo, pass in my vec dot data, something like that. And this will pass in x, y, and w, okay? Without me having to go my vec.x, my vec.y, my vec.z, okay? So again, that's the sort of the why I'm doing this. Now again, what the union helps us do is take on one data type or the other. So either float data 3 or this structure that contains x, y, and z. Okay. If I don't give this struct a name, right? You don't have to. I guess is what I'm saying. So that might be something that's throwing things off a little bit. So if I make it unnamed or anonymous in this way, I can just access it with x, y, and z. Just fine there. Yep. Does that make sense for folks?
Yes.
Yeah, awesome. All right. I have a video somewhere where I talk about this little trick too. If someone wants on Piazza, I'm happy to post it. Or of course you can search for it. But let's see, there is one thing missing here still. And let's actually get our code back here. That you might be wondering about, and that's why do I have a W here, which is this other kind of weird coordinate, right? This is a two-dimensional vector, so that would have X and Y here. Well, W is going to be our way of sort of cheating here, meaning that W is going to tell us, do I have a point or do I have a vector here? And typically the way that you do that is, and I think I have it on the slide here, so I'm just going to point to that. Let's see here. Maybe I didn't give it here. Oh, I do have it, yes. So if your W coordinate is equal to 1, then that means you're working with a point. And if your W is equal to 0, then it represents a vector. Okay. Now, why this distinguishment? Well, I've got to go to the whiteboard again a little bit here. And let's go ahead and draw some points here. And this will make sense in a moment because I'm going to talk about vector math. But let's say I have a vector here. And I'll just label it vector A. And this is about, I don't know, 5 in the X, 5 in the Y, and then it's a vector. So, well, I said that was going to be a 0 in the W coordinate. Okay, so 0. Okay, and I have a person here. Okay, let's draw a stick figure here, and they're at 0, 0, so the origin, and they're just represented as a point here, 1 here. Okay, so if I take this person right here and I walk them in this direction, right, which is what a vector is, something with a magnitude and a direction, then I'm effectively doing, well, where did I start from and where was the direction that I'm heading? So 5 plus 0, 5 plus 0, and then 0 plus 1 here. Okay, that moves my person here at the location 5, 5, 1. Okay, so what this 1 preserves, 1 or W equals 1, which is a new point in space. Right, this is where my person moved. Okay, does that make sense for folks? Okay, so let me kind of walk through a few more examples just to, again, make sense of this last W coordinate here and how you can use it in this library. Let's go ahead and let's pretend that I'm asking you, how do I get from Vancouver to, let me think about this. Yeah, Vancouver to Boston. I don't know. So I have some point over here. Again, I just got to make up these values here. 1, 5, and I said this is a point here, so a 1 here at the end. So let me just kind of illustrate this again. W equals 1. So a point, and let's just label this Vancouver. And then Boston is over here somewhere. 10, 2, 1. Okay, this will be Boston. Okay, so if I want to get from one location to the other, I need to subtract. And again, I guess it depends which way I'm going, from Boston to Vancouver, or Vancouver to Boston. But if I do, Boston minus Vancouver here, I'll do so 10 minus 1, so that's this coordinate. 2 minus 5, and then 1 minus 1. 1 minus 1. Okay, so what does that give me as a result? 9, -3. Oh, let me make sure I did everything in the right order. 2 minus 5. And then 1 minus 1 is 0. Okay. Okay, so what did this produce for me? Well, that means if I need to get to, well, I guess I'm going from Vancouver here. It depends on the order of the subtraction, right? This vector here, that is 9, -3, 0. Okay, so I moved 9 units this way, 3 units down, so -3. And, well, if this last value here is 0, that means I have a vector here, right? And that's what I've drawn here. Okay, so point minus a point, so something with a W of 1 here, well, something else is a W of -1, gives us a new vector. Okay, does that make sense? So we can kind of just use that last term here to figure out if I do something like a vector minus a point, do I end up with a new point or a new vector, right? You're just using the last sort of term. And that also sort of bars us from the one sort of circumstance, if I have a person here who is a point and another person here, you can't do a point plus a point. It doesn't really make sense. Point plus a point does not work. I think I have it on a slide later, so you don't have to memorize it. But right, if I add this point to this point, that doesn't work, right? I can tell you how to get from here to there. That's the vector, but I can't add. You just can't add a point and a point. So if you ever end up with w equals 2, that's a unit test where you can say, hey, this is a failure or unit mismatch or something like that. Okay, does that make sense? All right. So that's and that's following that example is actually kind of what I'm going to show you in the next slides here. But again, this is just sort of the chosen representation for our vec2. I think it's a pretty good one. We are in a way being secretive in our API, meaning we're actually storing 12 bytes of information, even though it's just a vec2d. Again, that's just going to be a design decision, but it gives us some of the safety, meaning that we have this w here, so we know if we're working with a point or a vector. Now, by default, in our constructor, you'll notice that I default initialize everything to 0 in our arguments if the user doesn't specify. Right? They can specify an x and a y, and if they ever forget to specify w here, it'll default to 0 as a vector. Okay, so that's just kind of something to keep in mind. Okay. So any questions regarding this? This is what you're going to be implementing for your homework, just filling out, how to do vector addition, subtraction, division, and a few of the other functions that we're going to talk about here shortly. All right, so some new C++ stuff and a little trick here. Hopefully that'll be useful. Here's just another example of an implementation you could start out with. This is something else that you could see, just having a vector 3D with X, Y, and Z. That could also be fine, although we really are going to use X, Y, and W. And then we could also use as a fake 3D vector if we wanted or we needed to later on. In fact, we will for our matrix multiplication. All right, so let's see. We've been going for about an hour here, so I'm going to go ahead and take a break on the live stream so that you can, review this stuff and ask some questions. We've went through a lot of the math, so I'm going to go ahead. We'll go through the slides and we resume, but let's go ahead and resume at. I'm going to do my time conversion here in about 10 minutes, so that'll be 1:13 for our Vancouver folks. All right, so we'll see you. We'll see you then.
没关系，你想哪里？有人在前面借这个插头。现在插头了，这个你看能不能用？你什么时候用啊？我今天3点半上下课，3点左右下课。你看你还需要用多久？
我用到2点10分，2点15。
可以，那你来15号你说。
你加一下我，可以吗？
行，到时候微信你。
然后我跟你讲。
可以，行，好，谢谢。
然后你如果是中途需要的话，你也随时跟我讲。
哎，没问题 ，OK， 好。 怎么感觉课听不进去，好烦。课没睡好。没有，也没有，也没有，没有什么好讲。感觉有点难集中精神，没有别的。
Yeah, it's I don't really mind too much. And it's just cold. That's tough. Are they okay? Yes. Like coffee. Exactly. Honey. It's getting cold this week. Yeah. Yesterday, I think my son got, and then my daughter got it from us. Yeah, exactly. It's the process of all time. Which grade was son? 5. 5. Yeah. Oh, he's that big? Yeah, 10 years. 10 years old. Okay, I didn't expect you so big.
iPad 好用吗？你用 iPad 就是只看 slide
我都想搞一个。
你又不能写代码呢？
电脑又坏了吗？
是的。
啊，对，
为什么？
日常坏。
对那个。
电子。你是还是上次那个问题？
这是另外一个。就
中毒了吧？
不是。
你
有点。
被吓中了。
对，被吓中了。
你看，当时那个 app 作业考终于搞定了，最后
你可以到那
要交的
拿这个扣。
对。
吐槽一下，好难啊！终于搞定了，特别是那个
有那个
3 Part 2，后面我还证明课上证明老师是错的。
我们学校那个学生照都有一个。
对，当 K 小1的时候校的。
对，那个好像可以。我还问了他说应该所有人都可以。
对，我们上课我们还刚才自己说的，这次晚上我会看老师一说好像是确实是不行的，然后后面就好像没有人，然后就感觉很无语。
他好像说那个 IT 可以够一些，就对。
哪一点的？
我还没看。
In this picture or my location of the location in this picture.
你们开始做下一个了吗？
没有，我在做的是。
我还没看，
你也没看？
我也没看。
不是那个周5要交，周4要交，周4要交，我还没开始。
什么？
下个作业是周4。
Colorful.
就 homework 4嘛，那个
Albert，
跟我没关系。
我还没开始呢，我昨天晚上前天都在写这个。
你们那个东西是不是有一条卷子？不是。
微差是啥样的卷子？
就你见过的，就是很像，
就是一只 all core synthesis 1、2，然
啊对
后那就感觉差不多。
差不多。他应该是 copy Richard 的材料给你，
但他讲的好很一般。
很一般了，质量还没到 Richard 质量。
Exactly.
Richard 上的 algorithm，
没有，我上的是 Boston 那边，
这边怎么样？
挺好，但老师挺好，我会看老师选课。
作业闹死。
我写40页，
最后考的。
每个月都写40页的，叫 seminar。
什么课？
也是 algorithm，是另外一个校区的，但是我觉得学到很多东西。虽然写完这40页，我感觉我大彻大悟。就写你对这个，就比如说 divide conquer 对它的理解嘛，然后你要举例子，自己设计题目，自己解，然后还有各种你要说服老师，真正理解透了这个题目，你要写个 textbook 一样东西。然后
我上的那个 algorithm 太水了，他都给我们考试是我们自己回去挑，然后做了就跟他说我只做了这一题和这一题就好了。
哇，这太水了。
对，所以我完全不知道你们这一次这个多 hardcore。
是拿 Richard 卷，但是没有 Richard 的 support。
是吧？我们他妈就全是读，看个视频，做个 quiz，看个视频做。
他们那个好像不是 Richard，
不是的，
对，全都是另外一个。
是 Boston 的。
对，我之前他用了材料，我看用的是波士顿另外一个老师的材料。之前不是就是学习开始的时候，不是有那个大学另外一个老师，那时候我看还以为我们变成 remote 课。还以为我们是 remote 教，不是那种教，吓死！后面才知道，后面我才知道他是没有改。
那个老师上课上到一半打写错，不知道为啥。
什么？
上课上到一半，还是在这一块或者说在打写
错。没有见过他本人。他之前是在印度嘛，然后他回来的时候我也没有来，帮你们上课。对啊。我也没有见过，
神奇了，第一次上了几十年的课，头一次见到上课上
解放一下。
对。
Yes, and it's 7 different things that make meals for our.
Alrighty, folks. Thanks for breaking with me here. We'll go ahead and get back to action. So any questions before we move forward, understanding some of the vector code or stuff going on? All right. Well, let's go ahead and keep proceeding forward. So, a few operations, things to keep in mind. And, I think the examples might be somewhat self-explanatory, and I'll usually have little examples here and just showing where you can find the code. I guess in our case it'll be vec2d or for times equal, but the idea is if you want to multiply a vector by a scalar, so to take some sort of magnitude and direction and extend it as sort of illustrated here, you can just multiply each of the components. If you have x, y, for us, mostly 2D, but of course, if you have 3D, you'll have a z here. So just multiply each of the components, and that's it for the implementation. Now, a new C++ thing, again, which is worth talking about, and again, I think is probably worth pointing out here is you'll sometimes see this, vector, whatever the type is, and then the ampersand after. And again, that just means that we're returning a reference here, so our actual object here. So let me see if I can show you in the code here, because I'll show you for the actual vec2d here. Let me go back here to our repository. In fact, you'll see this quite often here. And let me go ahead and just show you. Well, I could show you a couple examples because this one's already done, but if I'm returning something just a float, that's a value. But if I return with the ampersand, that's saying, hey, return to some actual data type here. In this case, I'm actually returning, well, whatever our x is, which is again one of our member variables here, and that actual address of this here. Now, this line here itself is a little bit wild. And again, you're going to say, well, why is Mike doing this? He's really throwing for a C++ loop here. Well, in particular for this math library, I wanted to actually show you like some actual engine code. This is what you kind of find. So as professional as I could get here. But so, and again, this is so I guess there's a few ways that I can sort of do this. Let me bring this back up here and just kind of rewrite that function, because there's quite a bit going on here in this little line here. And let's make it a little bit smaller so it fits. Or actually, let me just copy and paste this here. And let's keep the comments for now. And it's great that we have this on recording, so that's one of the, I like the format of this class that we can do that. So, I mean, let's just pull out this little part here. And, oops, sorry, for Vancouver, let's just play around with this just a tiny bit so that it can fit on the screen as big as possible here. Okay. Okay, that's better. Okay, so again, this is a member function here. And since we're returning by reference, I could write this a couple different ways here. And let's forget about this function because there's a little bit too much going on here. But let's just say I write a function here called getX here. And the return would look like just the actual x here. Okay, that's what we have here. But if I just put the ampersand, and this is one thing that folks get sort of lost in the C++ here, I guess. This is the address of x, so that's not an actual real floating number. In fact, I could just put x here, and this works fine. So this gets us the actual, this x here, like this. Okay. But the sort of strange thing that I've done here is, well, what I showed before, where I could actually just do data 0. But this would do the same thing here. So you can implement this either way here. Now, one thing to keep in mind, and does anybody, this is a question for our Vancouver folks, does anybody know what I'm actually doing when I use the brackets in an array? What actual operation am I doing when it comes to pointers and that kind of stuff?
I think you actually dereference it, then +0 on the pointer. Then,
yep.
And you can target this.
Yeah, it's actually the equivalent to dereferencing and then adding some offset here, +1 or 2 or whatever. So that's the equivalent operation here. So that's sort of the magic with what's going on here when I'm saying, okay, give me the actual floating point value here. So let me go and show you how I've written this C++ code. Is what I'm saying here is, give me whatever's at the address of x here, which is, x, y, or w. But if I offset by I, which I is an integer, so it's going to be either 0, if I'm just putting in 0, that'll actually give me x here. And that'll give me the actual value that's x. If I offset with a 1 here, so let's just pretend that I use my vec2d, I create some vector here, and I do vec at 1, so something like that. Well, my offset is now 4 bytes, the size of one integer. And that will retrieve me y. Okay, that's what it's equivalent to. And now why is it giving me y here, even though I'm getting the address of x? Well, let's look at our code here. The way that this data is actually laid out is, well, x is our first member variable, wherever that address is. And then what's the very next thing that's going to be 4 bytes away? It happens to be the same size as a float. Well, it's y here. Okay, so if I just move 4 bytes down from this position, I go here. Okay, and if I move another 4 bytes down, I get to here. Okay, does that make sense to folks? So again, just to kind of recap, when I'm retrieving the address of something here, address of x, and then I'm dereferencing it and saying, hey, give me, whatever lives in x offset by I, which I in this case could be 0, 1, or 2. That'll actually retrieve me the actual value that's stored here. And the optimization by doing float with an ampersand after it is that there's no copy. There's no new variable created. It's giving me this exact value here. Okay, and that's actually what we want when we use something like myvec, at 0 equals 7. I'm actually saying I want myvec.x to equal 7. Okay, I don't want to make a copy of this thing or anything else here. Okay, so that's the idea. This is pretty optimized code. There's, this is probably as complicated, I suppose, as syntax as you get in C++, because we're also using this operator thing, that's how we use the brackets. So we're saying, hey, use these brackets and then index into them. But that's the sort of idea here. And we want our math library to be super efficient. So I got to show you how to write super efficient code for this. Does that make sense? Any questions about this operation here?
I just have one small question. So what is x? X is a pointer, or it just?
So x is the actual. Let's look at it in our code here. It's this actual x here. Yep. You could write it out if it's useful. You could just say, this dot x. Give me the address of it, and then the brackets dereferences. And again, if you don't like the brackets, then you could do it sort of the manual way. You'd dereference it and then add I or something like that, I think is what's going to compile. Okay, does that make sense for folks? Yeah. All right. Other questions from folks on this? Yeah.
Hey, Mike, can you remind me, so when we do +1 on the address, do we actually just move by 1, or do we move by 1 times the data size?
Yep. Yeah. Thanks for recapping that. When we do +I, it's the actual data size. So if this integer is 4 bytes, we're moving 4 bytes at a time.
Awesome. Yep. And also, so you're saying that this is a very optimized, efficient way of doing this access of value. But can you show us an example of relatively not as efficient of way of accessing the data?
Yeah. So if we were just doing like float operator int I return 7, something like that, or now I actually don't know. I think actually when we do this operator syntax, I have to change the function a little bit to maybe something like this. I don't know, but the sort of unoptimized thing would be just to return like a value or something. What this is actually doing is making a copy of this value for the float versus this is saying, hey, just give me what's there.
Okay.
Yep. Yeah. So that's again sort of the point to passing we call this a reference because it's referring to the thing that exists. Yep.
Thank you.
Yep. All right. Awesome. Other questions? All right. So hopping back into the C++ stuff here. or sorry, the math. So recapping, that was just to get us to multiplication by a scalar there. Now you could write another multiplication function if you wanted, so that it's non-uniform, meaning that you multiply each of the components by something else. I don't have that for you, but you might have need to do that, so you're welcome to. And for this vector addition and subtraction, well, kind of showed this already, but when you add two vectors or subtract them, you just do that one component at a time. So that should be relatively kind of straightforward looking at this example here. Let's see here. And here's just, some use cases. So, eventually we're going to want to start using these math library to model forces and so on, which is what a vector is, a magnitude and a direction. So you can imagine, a character jumping and applying some force to them for that actual vector that sort of moves them along a nice arc or whatever path that you sort of go along. Okay, so that's the idea. That's just, again, motivating what we're doing with our vectors, something with a magnitude and a direction. So I kind of already went over this in the example. This was just the aside of what operations are legal. Again, adding two vectors is legal. Subtracting two directions is legal. A point in a direction is legal. Point minus point gives you a new direction, right? This is going from Boston to Vancouver. And then a point plus a point just doesn't work. And if you want, I won't say it's bonus points, but it's probably a good idea in your math library to handle that case. If you have a W, 2 points that you're trying to add, you could throw an error or write a warning or something. It's probably a good idea. All right, so as far as the magnitude of a vector goes, well, what's the magnitude? What's that actually mean? Magnitude is the length of the vector. Whenever we refer to that. So usually you'll see this indicated with the bars next to something. And I should also note that a vector, usually you'll see it indicated in literature. If you're just reading online or the tutorials, it'll be a bolded character. So here the bolded A means it's a vector A, as indicated here. Sometimes you'll see it with a little arrow on top. But anyway, this is the size here. So if you've got a X and a Y component, it's just those components squared and then the square root, because if it's a length, it has to be positive. And if you've got an X, Y, and a Z, or in the case of a 2D game, Z is just 0. So you just square all those components and take the square root. So that's the idea here. All right, and in the code, you'll see there will be a magnitude function that you'll have to implement, a member function here. But there's yet again another new C++ thing here called inline. Has anybody seen inline before or previously? You may or may not have, but that's actually going to be part of your homework and the warm-up that you can take a look at. And you'll see what that does. Also, again, I have a video somewhere if you're looking at C++ stuff, or I explain it sort of in depth. But it's a nice way for us, again, to really optimize our code. Now, I'll actually also note, thinking about optimizations here, square root happens to be a very slow operation. So there's ways that we might want to speed that up later on as well. But just something to keep in mind here. Okay, so how do we use magnitude of a vector? Well, there could be a lot of different use cases, but the one that came to mind was, if you had some ship or something and you applied a large vector or something that had a size of 5, maybe it's indicating that this object's moving really fast, so you move your screen more versus, if you're moving very slowly. So, these can be little ways to create kind of neat effects in your games. Again, none of this math is complicated, but, it's how we use it or apply these tools to make things, particularly interesting. All right, now when we work with our vectors, we tend to also want to make them unit vectors. However, so, that sort of negates this use case depending on how you want to use it. But usually when we're using vectors, we want to make them unit vectors. That means that their magnitude will be exactly 1. That means that they tend to fit nicely in a unit circle. So here's just a reminder of the unit circle. And that tends to make some of our other operations that we use easier if if we know our vector's magnitude's exactly 1, because it often saves us multiplications and these types of things. So you will have a little function to normalize or make a unit vector in your TinyMath library, and that could be useful. All right. Notation-wise, you'll often see this with U and a little hat on top of it. And again, computing the unit vector. Again, if I go back, here's the derivation, but you can see it's basically just divide each of the components of your unit vector by the magnitude. Okay. And then when you compute the magnitude, it should equal 1. All right, so that's the idea of unit vector. Again, usually we'll say it's normalized if it's a unit vector. Again, just meaning that its magnitude is 1. Okay. Here's just some examples if you're, rotating some object. So you can kind of see at the start of this image here over here, this guy who's throwing this projectile. It's kind of nice if you can just kind of target or rotate wherever that vector is, just using a unit vector. Now, in this case, you might actually want to preserve magnitude, but that was just an immediate example that came to mind where you might use this. All right, so a few little exercises here to think about things. I'll give you a moment to think about this, because can't define everything, but just thinking about our math a little bit. If I give you 2 vectors here, here's a vector A, here's a vector B, and I wanted you to compute the midpoint, go ahead and think about how would you do that? How would you get in the middle? And you can use the grid lines. It's not something I've talked about, but what do you remember? What would you do?
E minus A, then find the magnitude divided by 2.
Let's see, B minus A, find the magnitude and divide by 2. Is that right?
Yeah, it's the middle point, the magnitude of middle point.
Oh, sorry. Yeah, just the midpoint here.
Oh, just the midpoint. Okay.
Yep. Midpoint. There we are. That would make it a harder problem, I think. Yeah, so I think you folks got this here. Let me just actually advance it here. All right, just add the components, divide by 2. That'll give you the midpoint here between these 2 vectors. So again, just a little operation that you might want to, play around with. And I've listed the properties here on the top right just to show, the vector addition's commutative, it's associative as well. It's also distributive. So again, you can apply these operations. Again, do B minus A divided by 2, and you'll get the midpoint here. So again, that can be a handy thing for artificial intelligence to have a target in between 2 other targets, for example. All right, so quick trigonometry review here. This picture here is actually quite handy if you study it for long enough. I think I got it from this figure here, or here's at least the SOHCAHTOA. Have folks heard of SOHCAHTOA? Remember it? No, maybe not. Yeah. But basically this is the one thing to know from trigonometry whenever you had a lesson in a math course on trig or a course on trig. Trigonometry is the study of triangles. So the relationship between different angles and lengths of sides of triangles. And SOHCAHTOA is what we call mnemonic, or a way to remember the different trigonometry operations: sine, cosine, and tangent. So let me kind of move us along here, then I'll revisit SOHCAHTOA. But here's your triangle, and oftentimes what you'll want to do is we're kind of thinking about things in triangles, meaning that we have the length of the side, but this could also be 2 vectors sort of on the bottom side of this triangle, and then one running along this hypotenuse. So then we might want to know the angle between those two actual vectors here. So that's where our trigonomic functions are useful. So then, if we had some object here, we might want to be able to rotate it. I'll show you in an example in a moment. But the basic idea is, these are pretty well-defined operations: sine, cosine, and tangent. But if I use the sine function, I can figure out this angle by taking if I know the length of the opposite side over the length of the hypotenuse, I can figure out this angle. Okay, I can figure out I take the arc sine or the inverse sine function here to figure out that angle, or vice versa. If I know the angle and the opposite side, then I can solve for the hypotenuse, okay, using algebra. So that's where it becomes useful. And again, the mnemonic is this. If you ever need to remember, of course, you can look these things up. SOHCAHTOA. So just look at the first letter, SOH, for example. For sine, it's opposite over hypotenuse. Ka is cosine over adjacent over hypotenuse, and TOA, tangent, opposite over adjacent. So that's the idea with this one. All right. Now, one other law that's useful. Well, I suppose let me start with the bottom one. Folks have heard or maybe have memorized Pythagoras theorem, I'm assuming. Pythagorean theorem, right? You think about this when you're rushing a class, you take the hypotenuse, it's a little bit faster between 2 points. Right, so c squared equals a squared plus b squared, or a squared plus b squared equals c squared, however you want to remember it. That's actually a special case, right? That's for right triangles, right? We have a 90-degree angle here for figuring out the length of c. Again, that's just a special case, though, for the law of cosines, which here's the full sort of solution. When you have a right angle here, this term at the end, the minus 2ab times cosine of c, that just goes away, right? That's where you get your Pythagorean theorem. But if you wanted to solve for, let's say you had 3 targets in a game, or 3 artificial intelligence, A, B, and C, and you wanted to figure out, the angle between them or the distance, and depending on what information you have, you could actually solve for them for any triangle. So just another law to keep in mind here. All right. So there's a little bit of, nice examples or things that you might want to do. I'll actually just click on this link just to show you. I think this is the one here. Oh, actually, maybe, let's see here. Let me see here. Well, I guess this one was pretty useful. I had another one. Yeah, this one was pretty good, I guess. Give me 1 second. I think it's in my history here. Game Math 2D. I'll just show you something a little bit more interactive here. 2D engine. Here it is. Let me paste in the link here just so it's preserved forever. So you can also click on this link if you want to explore. And I'll bring in the web page here. Some of these different things here. It's a nice, I don't know who built this website, but Vector Math for Games. But you can kind of play around with interactively some of these examples here. So if you want to figure out the angle between 2 points, converting between degrees and radians, again, things that you've probably done somewhere in your life, figuring out angles. Let's see, angle between 2 points here. So here's the point with the origin, rotating vectors, all these sort of things. Now I'll introduce these again as we sort of need them when it comes to assignments. But again, it's kind of useful to know a few of these properties here. Length here, so you can kind of see how this is being computed. I just thought this was a nice interactive way to see what's going on here. Let's see, this is normalizing. Now some of these visualizations we'll actually want to read probably to figure out what's going on. and I'll show you in a moment. But anyway, just a few interactive things there. And this is just my aside that, again, we tend to think in radians when coding, so it's usually pretty useful to have a radians to degree function or degree to radians. Oops, let me correct this spelling mistake here. Radians. Again, why that is, well, most of the math functions are programmed in radians. Yeah, that's part of the reason. All right. All right. Any questions on some of that? That's the world's briefest trigonometry refresher, but any questions on these things here? All right. If you don't remember SOHCAHTOA, it comes in handy. This is a thing that's going to come in handy for you when you actually are implementing your game, I think, more so than the actual engine part, right? The math functions are built for you. So there's nothing we really need to do other than include math.h or cmath.h. All right. All right. A few other tools that we'll want to add here. So back to vectors. And one tool is projection. And this is useful for computing dot products. And I'll actually just show it in a demo rather than going through the text. But the idea of what projection is, if I have two vectors and I want to project one onto the other, let's give these demos here. So again, this is a nice sort of interactive text here. And this is the useful demo 3.4 here. So I've got a vector u and then this vector v, and I'm projecting w onto this vector. So you can kind of see how it grows or moves along. And the example or why you might want to use this is pretend that u here is a skyscraper, v is the ground, and w is the shadow. Right? So if I have a really tall skyscraper that's leaning at an angle, right, it's going to cast this sort of shadow. Or maybe if I lean something all the way like this. So that's one way to use the projection. Right, it's often used in games and graphics for lighting equations and casting shadows. The other, you might use this in a game if you have some projectile, for instance, and it's coming at this sort of angle and you want to, drop something onto a surface, then you could project it onto that surface. Okay, that's the sort of idea. And the fundamental idea when you're projecting u onto v is you're basically picking a point along v where you're, casting that shadow or dropping something along this path. So the other way to think about projection is you're reducing a dimension. Okay. Have folks been to the movies and seen a movie played on a projector recently? Or I guess I should ask, have you ever been in class and, there's a projector? That's sort of the same idea, right? We're projecting, what would be 3D onto a 2D surface. So that's the idea where projection comes from, going from 3D to 2D, or 2D in this case to one dimension, right? If I view v as just a numbered line here, and again, this is worth making clear here. Let's just, let's get rid of this illustration here. As beautiful as it was, it's time to go. All right, and again, this is a thing that probably when you learned math that, it's probably been so long. It's been so long for me, right? You learn about a number line, right? 0, 1, 2, 3, etc. And so on, right? This is sort of one dimension, right? You can only go this way or this way, right? If you're walking. But of course, we're talking about Cartesian coordinates this time. So we have another plane here. So here's x, y, okay? But again, if I have a vector and I want to project this point down here onto my number line, let's actually do it in a different color. Right, that's got to tell me where I'm landing on this dimension. Okay, does that make sense to folks? That's what it means when we're projecting. Okay. So the actual math and how to do this, here's me explaining my analogy. And here's about, casting a shadow. Let me actually, here's the 2D engine demo again, if you want to see exactly. Let's see here. Here's the actual math here. Here's the actual equation. Now, what is this saying? Well, let me try to say it at least once clearly for the recording, that I'm projecting vector u onto v. So I read this projecting onto v, vector u dot v, and this is the dot product, which we've got to talk about that, over, well, the length, right, the bars here, or magnitude of v squared times v here, okay? Okay, now there's still a few new things we need to figure out. What does dot mean? Well, that's sort of the next note here, dot product, okay? How many folks have heard dot product in a course before? Yeah, some folks, yeah, you've probably heard it. It's relatively easy to compute, actually. And I'll tell you why in a moment. Here's the formula, right? It's given to us. But again, it's fundamentally just understanding what dot product's for. Dot product's for determining how similar two vectors are, okay? So you can kind of look at this example on the left. I'd say these vectors are fairly similar. They're sort of moving in the same direction, right? If this is you and your friend, you and your friend V over here, you're walking alongside each other, right? So you're very close. Very similar. But on this side, you're quite different, right? You're sort of heading in opposite paths here, okay? So that's the way to think about the dot product. How similar are two vectors? And, what it's actually measuring is the angle between the vectors, okay? For how they're traveling. So let me give you a gaming example, then I'll get to the derivation so you can solve projection. But the idea would be, if you have this character here for Mario Kart, a racing game, and you're driving over a booster pad here, that's an example I like to use, you get sort of a faster boost if you drive directly over this vector, right, in this direction, okay? If you're coming the opposite way, you don't get any boost, but if you're moving similarly, you would take the angle or the dot product of what's blue here and what's red here, or the arrow above this character, and that's how you could, use dot product here. Figure out the angle between, or how similar these two vectors are, okay? That similarity is measured between a range of, -1 and 1 if we're normalized, and, you can use that as some game mechanic, okay? Does that make sense to folks? Okay, awesome. The other place where you use dot product a lot, especially in 3D computer graphics, is for lighting, again, to figure out if there's some light source directly over, a surface. In 2D, we don't have to worry about that as much, but let's just go ahead and see how we use this. How do we compute the dot product? Well, each component I multiply, so the x I multiply, the y's I multiply, and the z's I multiply, or however many components you've got. First component times, you multiply those and add them to the second component that are multiplied and the third component that are multiplied, okay? That's the idea. And then that gives you some scalar value. Now, this tends to work out best. You'll notice that these two vectors are not normalized here. So it tends to work out best if we normalize our vectors before multiplying them. Because if we normalize them, just looking at this example, I get 2 times 8, 16 plus 14 plus 8. So this value of 38, I don't really know what that means, but if I normalize my vectors so that their magnitude when I multiply them is 1, when I take the dot product, I'll get a range between -1 and 1. If I get a value of 1, that means we're moving in the same direction. A value of 0, they're perpendicular, and a value of -1 means we're moving opposite direction. Okay, so again, you can kind of imagine this in a game if you want to see if two objects are moving, similarly, or for a lighting calculation or these types of things, and you get a nice value between -1 and 1, that range. Okay. So that's the idea, and here's just some more illustrations. There's a really nice series of videos here that I've linked in if you want to see more about dot product and just how it sort of works. In 2D, I think it's relatively intuitive. For those of you who are going to take graphics with me later, though, this is, nice stuff to know, or for those who have taken graphics with me already, well, I guess you've seen this, but it's a nice visualization. All right. So with that in mind, if you want, you can kind of derive the dot product from our sort of projection formula. But what I'll tell you here, and let's see here, I think I've got the derivation written. This formula over here, if I tell you that my vectors are normalized, so A and B are normalized, well, this term just goes to 1. And then I'm dividing by 1. So you end up just getting A dot B equals cosine of theta. And here's the sort of whole derivation. All right, so anything that I'm taking the magnitude of goes to 1. And that makes things relatively trivial. Okay. So the angle between two vectors is A dot B. And then you can take the arc cosine to solve for the angle. Okay. So that's quite nice. All right. So a little bit more supplement on dot product if you need here, just some more examples, some more visualizations. We won't go over that forever, but again, use cases, right? It's useful. This is a 3D example, equally applies in 2D though. If you had a character sort of chasing another one or wanted to see if they're, facing each other or in a similar direction or not, right? You could use dot product to sort of figure out, well, if this character is sneaking behind this one, right, they need to be moving in the same direction. So, right, this artificial intelligence character can't detect this guy here. Okay, so that's just an example. All right, and then as I mentioned, dot product's used a lot in lighting calculations. This would be true in 2D as well. I know I'm showing a graphics example, but if you have a light casting onto a surface in 3D, right, you'd figure out the angle between what's called a normal on a 3D surface and the light, and that would that angle difference would tell you how much of this light's hitting this surface. Okay, and here's just an illustration of that. Okay, so how dark the shape is based off of where the light source is and the angle between this blue and this green vector. The blue one swinging around and the green one facing up and down. All right. All right. How are folks doing? Any questions on dot product? Nope. All right. Not seeing anything. So let me talk a little bit about cross product. Now, again, I'm focusing on us on 2D here for this class. So I'm going to kind of skip the 3D part here, but here it is. Cross product of two three-dimensional vectors gives us another perpendicular vector. So I'm going to kind of go through that. Again, you'll see this if you take me in graphics. This is really important there. But what about in 2D? Well, there's a nice video here. And basically what a 2D cross product gives you, or 2D wedge product is probably the most correct way to see it. And you can see the derivation in this video or highlighted here. It basically tells you which side of the vector that you fall on. So it's nice to sort of, for orientation purposes, to have this function and see which side do you fall on. Okay, what does that mean? Let me go ahead back here for a moment to that nice website, just so I can show you. It's a little bit easier to show you visually this 2D engine thing. Let's see, cross product. Okay, so here's how to do it in 2D. What's it mean here? Well, actually, let's see. I thought there was a better. There are some nice examples on this website of like, you can just kind of play around with, like rotating to a target. Again, this is why you're using this sort of stuff. You say, hey, the angle is, big. Let's reduce that angle, right? Then you can kind of see this middle arrow turning towards or away from this object, right? And with a little bit of object logic, you figure out, do shrink the angle, or if you're on the opposite side, which direction to go. And you've got some pseudocode. I was trying to find, I think there was a cross product. Yeah, this kind of shows it here. What's in the, I think this is showing, it's kind of showing, but the idea would be where the blue arrow, or I'm extending it to the right, this would be sort of a test of which side am I on. So if I took the cross product of these two vectors, the blue one that I'm extending out, and I believe what is from P to T here, you want to know, are you on the left side or the right side? Well, if I'm over here, I'm on the right side. If I'm over here, I'm on the left side here. So that's what it's kind of showing me. Although I guess they don't have a great example, but that's the idea. The video shows a nice example if you want to see, again, just how to use cross product in 2D here. So that's just a little aside on that here. And there's a little inaccuracy. The video calls it 2D cross product. Just call it 2D wedge product. I think that's a little bit more accurate of what it actually is. Okay, so normal vector, again, for 3D graphics, more important. Again, I think most folks are going to be doing 2D here, but here's normal vector. Again, that's just something that's perpendicular to a plane. Again, we have the same thing in 2D, a vector that's perpendicular to some surface that we might want to use here. But we're not really doing stuff with triangles, so I'm going to skip over that portion here. All right. Okay, so with that said, the next topic that I want to talk about, and then we'll take a break here in a moment, is matrices. And again, this is a collection of values. So basically, this is a compact way to represent some transformation. Now, how to read matrices depends on if they're column or row. If they're a column, that means I'm reading them up and down. If they're a row, that means I'm reading them left to right. For the most part in this class, we'll sort of think in columns, so looking up and down. And this is a compact way to represent transformations. If I want to translate a point or scale or rotate a point, I can do that with one matrix here. Okay, so you're actually going to have a matrix class here, at least a basic one to set up for now. And set up, so it's going to be 3 by 3 since I'm, again, defaulting pretty much everyone into doing 2D games here. But basically a way to construct different matrices and apply operations to transform a sprite. Okay. So how do we transform and move stuff? Well, in order to move something, and I'll talk about this again because we are going to have to revisit some more math things, but we need some operations for matrix multiplication. So what's matrix multiplication mean? Well, taking one of these matrices, multiplying it, and basically that's an operation of taking the dot product of the first row and the first column and producing the new result here. Okay, so I could refresh a little bit on matrix multiplication here, but and all of our matrices are going to be 3 by 3. So you won't have to worry about if they have different rows or different column numbers like you might have had to before, but that's the idea. So we'll want a matrix multiply operation here. All right, and again, as mentioned, we won't really have to worry about this because we'll have 3 by 3 matrices only. But the important part that I have to get to and tell you about is that the order matters in our matrix multiplication. So if I multiply matrix A times matrix B, that's not the same thing as multiplying matrix B times A. Okay, so the order matters. You can think about this as concatenation. AB is a different string than BA, and that affects the order of our actual transformation of our objects. Okay. So meaning that, again, if I have some object here and I want to transform them here and then rotate my object, I don't know, 90 degrees or something so that they're in some other orientation, that's going to be a lot different than if I rotate the object first and then, move them over. They'll land in some other location, right? Here versus here, for instance. Okay, so that's the idea. Okay, so order matters. All right, that's all I need to say about matrix multiplication right now, because that'll be enough to get you through the assignment. But let me go ahead and pause, because I think I've given you all the math tools you need, but is there anything we want to revisit or take a look at here? So we'll have a data structure for transformations. We'll build out some as we need them, but we just need the ability to multiply first. And then we've talked about a few topics like vectors, cross product in 2D. I skipped over 3D. Dot product, where we'll use it. Angles, some of these different things, and so on. Any questions on this stuff? Yeah.
So what's the use case for matrix multiplication?
Yeah, let me get to matrix multiplication here. So what we're going to end up doing, and we can actually get away with, I mean, all the matrix is taking two vectors here. Well, how do I want to say this? A matrix is a way of compactly, so this is, a matrix is a way to compactly represent some sort of transformation. So this matrix here, which is the identity matrix, so it has ones across the diagonal. Let's say this is our player here. And what we can actually do here is, well, when I'm reading this as a column matrix, so this is the first column, and this is indicating my X sort of orientation. And this is the operations that I'm sort of doing on the Y-axis, okay? So what does that mean? Well, I can actually create a rotation here. And how do I rotate something? Again, if I sort of think about dividing this into two operations, what I'm doing on the X-axis and the Y-axis, well, that's sort of figuring out how do I move along this axis here, and again, this axis. So for X, that's going to be cosine of theta here. For Y, that's going to be sine of theta, and these are just zeros. So if I multiply my current position, which just might be, whatever this orientation is, identity, my hero is at the origin here, by some angle here, which is my rotation, this is telling me how do I move on the X-axis and the Y-axis so that I can move around here. Okay, so how am I rotating? That's what this rotation matrix is capturing. And as a function, how we're going to write this would just be void, the angle that we want to rotate, and then maybe do we want to rotate about the, the X-axis, or maybe we want to just rotate about the Y-axis. And if we had a Z-axis, if we wanted to rotate about Z. So matrices make that a little bit easier for us to do. Now we could just do everything with vectors, though, meaning that I could have a vector here, and I want to just rotate it 30 degrees, in this direction. We could also do that, but matrices are a little bit more compact, and they better capture translation. And this is where we're going to need a 3x3 matrix, which I'll explain in another lecture when we get there. We'll actually need a matrix that looks like this. And basically, again, this is going to be our offsets here. So right now, there's no offset. I'm just at the origin. But if I make this a value like 7 and 8, that's going to tell me to sort of do my operations from here and then, rotate 30 degrees or whatever. But that's the idea. So we'll revisit using these actual matrix transformations and building those in a little bit. But that way we just don't have to, our vectors are basically each of these columns that we're multiplying, and that's it. Does that make sense or help clarify? Yep. Yeah. Anything else? If there's something else that's unclear, let me know, and I at least want to capture the idea now, and if we're going to expand on it further, I'll let you know. But we are going to revisit, building a rotation matrix and then a transform and all that kind of stuff. All right. Well, with that said, let's take another break, and then I'm going to go over just a few topics that I would say fall in the sort of more advanced category bin, but I think are going to be important for you as engine programmers. They're optional for the homework, but I'd still like to expose you to them. So let's take another 10-minute break here till 2:16, and then we'll resume.
Oh, Professor, are you here?
Yes. Yep.
Oh, I just have a question. So are you teaching computer graphics next semester, like in fall or summer?
I am. Yeah. I think there's a little bit of a mistake in the schedule right now, though. Let me check here. Because I should be for summer 1 doing computer graphics. Summer 2, another computer graphics course. And then summer full, I should be doing a geometry course here. Let's see here. Although it looks like it's still not updated. Let's see here. I think summer 1 is correct.
What's the difference between a geometry course and a graphics course?
Yeah, so the graphics course is going to be more so like, here's how to use OpenGL, work with meshes. The geometry course is going to be more, here's some data structures, here's how we represent meshes. It's more of like an algorithms course. It's still programming based, but I think it's more like mesh representation for like AutoCAD and those types of tools. Like building a 3D modeler would be like a good course project for the geometry course. The graphics course would be more, building a game is, an example, I guess.
Great, thank you.
Yep. Yeah, so this graphics is correct for the summer 1 online. That should be good.
Let's just check. I mean,
I gotta talk with my advisor though. I read off the electives. Yeah, because you can only do 2, right? Electives.
I don't know.
I wasted one on some other classes because we have only so little classes.
Yeah, I think you can talk with him.
Yeah, probably talk to Maya or some person.
Oh, you see, this one is.
Because I don't really, I don't know, because
I think as long as you, I think we were just with 40 credits, you're concerned.
32, like
32, or 32 to like 44, something.
32 to 44, but then I'll pay
Prepare
extra, right?
to graduate event.
Because all I left are those breath calls.
This is the photo and.
If they don't offer to me, I
The
understand.
upper council. Oh, I registered for this one. Yeah, me too, but I didn't register for the purpose. Yeah. Yeah, so I saw like there are 2 different things. Okay, yeah, got it. I don't want to be the first one. Just want to get it. Graduation ceremony. I guess. In Vancouver. Oh, so I thought we had like a ceremony in Boston. Everyone go there. Yeah. No, I heard that like all of us has been like to make it. That's what I heard. Apparently I'm not chosen. Actually, because of the situation, I can't go to US. Do you have a Exactly. No chance for international. Yes. I got my visa, like a tourism visa last December. It's for 10 years, which is pretty good. But like lots of my friends, because
Okay, let me talk.
I study machine learning, so they got like checked for the. I got it. I didn't get checked. I just get it after 2 days, 3 days.
Just graphics.
Don't go to
You're taking the graphics.
I honestly don't know. I have to ask.
2 weeks ago, me and my boyfriend went to Seattle. My brother, my cousins are staying there in Seattle. They're living there. So like,
If it has to be extra, then
yeah, weekends, at night after the sunset, I was like, in United States, after sunset. Why not? It's just simply dangerous. I saw people on the street, they walking and they look so angry. I was like, oh my God, honestly, really. I feel like they're not.
怎么了？
Power 有问题。
Way friendly.
他有问题。 你说的话都害怕。你又害怕了。
So if I find a slightly expensive car, I can drive it for more years. If I buy a car that I can afford, so I can pick up and that you like it. Yeah, but I like it. I just wear like I'm your color. Yeah, I don't know. That's it. I don't know. Much
No, it is. It is. Yeah.
What if I want to buy
Enjoy the life.
Okay.
I like it.
Yeah, I say too much on this. Just enjoy.
对。
Sorry. Yeah, what if I can afford it?
上了课我问他我
You need a job. I need a job.
那个问题比较长，不知道他看不看得完，可能看一眼啊，这个太长了，对不对？
I mean, the salary is not so good, but really get paid.
他是先把短的 然后50点。
That's what. Yeah, I don't have time to change city, country. You don't want to?
然后他讲那个有问客户。
I just best place in Canada. And
你为什么？你现在你为什么不现在问？你为什么不现在？我时间不够啊。
Alrighty, folks. I'll go ahead and get us back in action here for the final stretch here, and then we'll get started on your homework. And happy to talk about other courses, and I'll probably make a Piazza post too, or maybe an official announcement next lecture as far as courses. I'm excited about this summer for those registering. Hopefully, can get some of you back. But all right. So with that said, so I mean, with what I've given you so far in lecture, hopefully it's a roadmap, enough of the resources and so on that you could complete your homework as it is now. So your homework's going to have 2 parts. We've talked about this struct here, some of the C++, why it's a header file to make things relatively easy. And the assignment itself is divided into 2 parts. The first part is just exercises on linking, kind of project management. I think it'll be, super useful stuff to just, again, some of this stuff you just got to know cold as a engine programmer or software engineer, and it'll, I hope serve you for your entire career. That's the goal of, a lot of the stuff in part 0. And then part 1, again, is the implementation work here. Now, part 2 is sort of just a series of optional, activities, again, meaning you don't have to complete it. But I at least want to give you a quick overview of, some of the stuff that does go into game engines, and specifically the math libraries, which is this idea of instruction level parallelism. So the idea is, some of you might have heard or maybe have used in other courses, CUDA, OpenCL, other GPU programming tools. And the idea is, your graphics card has lots of processing power, parallel processing power. And while I'm not going to specifically talk about CUDA or OpenCL in this course, the idea is our modern processors, just the CPU itself, not even the graphics card, has a lot of parallelism built into it. And what I'm kind of highlighting here in this picture down below is, and you kind of have to look close, but you'll notice these things called ALUs. Does anybody know ALU, what that stands for? Or maybe, I guess the better question is, how many of you folks have heard that term ALU? Might not remember the acronym.
Algorithm something, unit something.
Yeah, arithmetic logic unit. So, and I'll actually, let's see, do I give you the, I don't like these 3-letter acronyms here. So let me just put ALU equals arithmetic logic unit. That's basically the thing that does the math for you on your machine, right? The addition, subtraction, all those operations we've been talking about. But again, what you might notice here, and you have to have really good eyesight if you're in the back, but there's more than one on your machine. In fact, there's usually dozens and different types, right? Ones that happen to handle, floating point numbers, some integers, and so on. And the point is we want to exploit that parallelism. So we say that our architectures, most of the laptops that you have, even your cell phones, are what are called superscalar processors. And that means they can process more than one instruction at a time. So that means, we don't have to think about our programs as executing one line of code necessarily at a time, but, lots of stuff's happening in parallel. So this is, a representation, pretty technical representation, actually, of the actual machine, all the different components in here that you'd probably see in a computer architecture course. But the idea is this execution engine down here, which does all your math and the actual work, is highly parallel. Okay, so that's the only point that I'm trying to get to. And if you want, you can actually, click on this stuff just if you're curious. Some of you might know if you have an Intel or whatever processor, there's this fun site, Wikichip, and you can find out, whatever your processor is. Apple's kind of secret, so you might not find Apple. I don't know. But you can find one that's similar, and it'll give you a pretty good diagram of, all the parallelism available. So the point is, you have 4 ALUs, specific things for doing division, subtraction, etc. And again, I'm not going to read you this wall of text here, but again, we want to exploit that parallelism, and I call that instruction level parallelism. So things like, adding, if you've got a bunch of operations where you need to add. So let me go back here and just let me be explicit about what I mean about this. Let's get rid of this stuff here. Something very parallel that we've been doing here is, well, if I've got point A here and point B, and I told you, point A has an X and a Y, and point B has an X and a Y here. Right, wouldn't it be nice if we could just do x plus x1 and y plus y1, right? There's no reason we can't do these operations in parallel, right? They're distinct. The data's, and each of these things is distinct here. So that's what I mean about instruction. Let me try to write this neatly. LP, instruction level parallelism. We're doing things in parallel, right? These operations can happen at the same time. A way to indicate this in the code, sometimes you'll see this again, if you're digging around, there's a keyword, it's in the C language, which, means it's also in C++, called restrict, which is sort of telling the compiler, hey, parallelize this code if possible. So I could actually put restrict here. And, if you're just adding, again, these values in an array, and they're, A has no dependence on B or vice versa on C, then you can do that in parallel. Okay, so that's the idea. And compilers have gotten better at doing this automatically. There's a library called OpenMP where you can basically just put this pragma OMP and then type SIMD in front of it, and it'll try to parallelize this for you. Okay, it'll do sort of the hard work, or what I'm about to show you here. And again, I just want to give you a sneak peek of what's possible here. Now, what's going on here? What's the idea? Well, this is what's known as single instruction, multiple data. Okay, so let me just illustrate this. Again, the idea is, if I'm adding vector A here plus vector B, there's one instruction here, which is add, and multiple pieces of data, right? There's a X and a Y component for A, and an X and a Y component for B. Okay, so that's what SIMD means for single instruction, multiple data. So this has been around for a while, since it's as old as time, I suppose. Computers since the 70s. A lot of this sort of parallel stuff really has been around since at least 2003. So there's no reason this isn't something we couldn't use on any computer. And the examples that I'm giving you are for this thing called AVX2. So I'll explain what that is. And here's the basic idea, or how you would use this in a game engine. So the basic idea is you have something known as a register, and that's basically a collection of bits or bytes. Okay. So a register, you can think of like a variable, but it's really a register. It's just some collection of bits here. And maybe you can fit 8 floats in that register. Okay. And you want to perform a single operation on all that data, all these 8 floats here. That's the idea. So let's kind of walk through it. So what does this code mean? Well, first and foremost, the variable at the front, underscore underscore M256, that means we have 256 bits of information. Okay. And I have this variable, or this thing I'm going to name ones, and then another one called count. And then I'm going to be able to set these 256 bytes in my ones with 1 here. So all of my 8 floating point numbers. And then I'm going to do the same thing with count here with 1, 2, 3, 4, 5, 6, 7, 8. Again, 8 floats. They're 4 bytes each, so 32 bits. 8 times 32 is 256. Okay, so this is the data that I'm able to pack into 256 bits of information. The single operation that I want to do is subtract. Okay, so there's a subtract operation here. You can see sub here. And I want to subtract ones from count. And then if I print out the result here, which I've casted to a float, this is kind of a weird trick, but again, we can see we're sort of offsetting whatever this float is, 8 bytes at a time, 1, 2, 3, etc., to get the 8 different bits here. Okay, and then you'll actually see what this prints out. I don't think I included it here, but this should print out 0, 1, 2, 3, 4, 5, 6, 7, etc. Or actually, that's exactly what it'll print: 0, 1, 2, 3, 4, 5, 6, 7. Okay, so that's the idea. And what's the performance boost? Well, instead of doing 8 subtraction operations, I just did 1. Okay, so this example is included in the GitHub repository. It's included in your assignment, I believe, as well. And there's a few more operations as well. So all I'm really saying with these single instruction, multiple data operations is we want to think about things in terms of bits or bytes. So we're sort of counting how much data can we pack into these special registers in our CPU. So in most cases, if I have 8 32-bit integers or 8 float values or double, which is 8 bytes, I can do 4 of those at a time, which, these are kind of convenient numbers, meaning that 4 doubles, that tends to be, our VEC3s, right? We have 3 doubles or maybe 8 floats. We can pack information into these special registers and save, again, 2 or 3 times the amount of time in some cases. Okay, so this is just on the math here of how many bits can I fit in these registers. And just another visualization. So I'm going to kind of skip through this because this is just showing you again another visualization of how much data can actually hold. But again, the advantage is we can generally parallelize our program here. Let me get to an example here. The disadvantage is, well, we have to think about it. Our code gets a little bit weird because we're using these single instruction, multiple data, instruction sets. We have to make sure that things are right. But here's sort of the motivation for performance. Right, using these AVX2, roughly, you can get 200% increase in your math library, which, well, if you're doing a lot of math, which that's what games are, that's a pretty big deal, right? You get twice as much stuff on the screen or whatever. So anyway, these are just kind of ballpark estimates. So if you want to work through the tutorial, I'll sort of stop at this point, because you'll read through the part 2 if you want, but this is just a guide here on how to read some of the types. It's repeated in the text here. But again, how many bits you have, and sort of how to decipher that in the conventions. Here's the header file that you include. You can actually look through it if you want. And then there's just a little experiment to see if you think that this is worth it. So, math operations, you can sort of, here's a benchmark again included of just sequentially adding a bunch of stuff to 2 big arrays versus parallelizing our data structure, right, with AVX. So again, here's just explaining what happens. Here's another parallel example, and sometimes it's hard to tell. Now I've got an benchmark here just to kind of get you to the end, but in this little example here, I show that the parallel version's about twice as fast, roughly speaking, I should say. We want to actually look at the real time. So actually, it's not even twice as fast, maybe 33% or 30%, because it does take time to use these actual registers that are special and put the information in those registers. So there's a little bit of a trade-off, but I'll still take 30% speed up. All right, and then there's some nice tools, a nice tool, Compiler Explorer, if you want to actually paste this code into and run. But here's the takeaway that I want you to get from this, because I'm not expecting everyone to go through this exercise. You're welcome to, but the takeaway is most math libraries will use SIMD instructions. So common ones like GLM's a common one, has these available. And then the second sort of important takeaway is I think every interview I've had for game engine programmer positions, they've asked me if I'm familiar with SIMD instruction set. So you at least need to be able to explain it. It always comes up. I've never had anybody actually quiz me on it, but it's almost always come up as a bonus. There are some exercises for you. Is it important for this class? Not really implementation-wise. Is it important for your career? Maybe. So that's why I've included some exercises here. And they're written in a tutorial way, so you can do them, one after the other, and enjoy those. So that's what I've got for you. I know that's a quick crash course, but I think it's an exercise of, if you finish the math library and you're trying to figure out what to do, it will serve you well, at least if you get to the interview point and can say, yeah, I've done at least a little bit. I know what instruction level parallelism is. Like I said, I've always been asked. I've never been quizzed on how to actually do it, but it's a good skill to have. All right. So let me pause there and take questions. Any questions on the SIMD, single instruction, multiple data? I know I went through a little bit fast, but it's kind of optional material, I suppose.
Yeah. So the register set is located on the CPU or on the GPU?
Yep, this is all on the CPU, actually. Now, the GPU, if you do GPU programming, has the same, they call them, SIMD processors. This is the same idea, except in a GPU, you just get hundreds or thousands of them. On a CPU, you get, 4, something like that, maybe 10 or something on that scale. But so this is all on the CPU, which is kind of neat.
Yes.
Mm-hmm. Yep. And most all processors, again, are going to have at least AVX2. Maybe if you're on a phone or something, you might only have 128 bits. But again, that might be enough for us because, right, we're working with VEC3 or VEC2D with a third component. That's it. Yeah. What else? Other questions from folks?
Well, another question. So yeah, this register also have so for Apple also have this register, right? For Apple M1 chips.
Yep. Yeah. Pretty much every machine has this. I think they're pretty consistent. Last I tried on my Apple, this worked fine. Actually, I haven't tried on my M1, but it should be the same. As far as I'm aware. Maybe the instruction names are different, but the idea would be the exact same.
Question.
Yep.
So for the inline keywords, what sort of functions are the most suitable ones to use inline?
Yeah, let's see here. So for inline, basically functions that are small. And the reality is the compiler will figure out for you if it actually will inline. So it's not guaranteed. You can force the compiler to inline if you want. In fact, I'll post on Piazza here these videos. Let's see here. So here's one here. Let me see if I can just sort of jump to the right spot here. All right, so using inline, this is the tool Compiler Explorer, which is an online sort of IDE. I just want to show you. Oops, sorry. I skipped around a little bit too much. There's a way you can force the compiler to inline if you're sure. Sorry, I just want to get to the actual code here. There we are. So you can say always inline. And the trade-off that you're making when you're inlining, since it's essentially copying and pasting in this code, this function everywhere that's called, is if you call this function a lot or very frequently, that's going to make your code size very big. And that could be problematic for either the size of the code or just how much data is sort of in your pipeline potentially. So again, candidates are small functions. Usually the math functions that we're using are good ones to inline. So, you know, computing the magnitude, adding 2 vectors, those kind of things are fine, I would say. Yeah. And I'll share this video somewhere. Let's see, other questions, comments on anything? No. If not, let me come on the big screen here. And see if there's anything. Anyone want to discuss anything? Otherwise, I think we've been over the homework, so I think that's relatively clear. The first part's reading. The second part's going to be, again, implementing the TinyMath library. Your objective with TinyMath, actually, let me show you that just to capture it. For, again, part 1 here, right? You'll actually come in the library and, oops, yeah, there's no CPP file. There's just the header file. So you'll find a bunch of the to-dos here. So you can just search to-do, and I think I did a pretty good job telling you, you know, what you need to do. I guess, you know, implement this function for matrix multiply or whatever. Most of these, again, feel free to use your notes or whatever. Again, the point is for you to understand what the tool is. But then what I'm going to actually ask you to do, as far as some of the work is, there's a tests folder here. So if you go to test.cpp, I want you to write some unit tests to prove that this works. So, you know, create 2 vectors, you know, add them together, and then check if the result, you know, actually works here. You know, do you actually get a result of 1 here? Okay. So that's sort of the task. And then to actually run it, what I've included to make this a little bit easier is a build_tests.py. So let's see, I believe I have this up and running so I can show you, or at least capture it on our recording here. So if I cd into assignment 4 here, part 1, I'll make this bigger. All right, you can actually do Python 3 build_tests. You'll get a new program here, /program unit tests. You'll run it, and if it's passed all of your tests, well, in this case, I failed because I haven't done anything. You know, you'll have some confidence that your program is working, basically. That's the idea. Okay, so that's how you'll actually run your assignment. 1 or 2 things to note about, and I'll also share on Piazza because I think it'll be useful. When it comes to comparing floating point data, does anybody know why this might be problematic? I mean, this particular example is okay, right? If I add 1 and 0, I'll get 1 here. But does anybody know what's kind of tricky about floating point math? Yeah, what's tricky about it?
Sometimes they can have some, I don't know the exact word, but like leftovers. So sometimes it might not be exactly 1, but you know, 1.00001 or 0.9999.
Yeah, exactly. So sometimes when we add stuff, I don't know, maybe I can do it in Python or something. Right, if you do, I think if I do, you know, x equals 1 divided by 3, let's see here. Let's see if we can. X equals 1. Hold on, let me. Python's not going to cooperate here. That's why we're using C++. No, I'm just kidding. Let's see. X equals 1.0 divided by 3.0, right? So let's print out X. Okay, this seems okay. Let's do X or Y equals. Let's see if we can break it here. 1.0 divided by 11.0. Okay, print Y. Actually, Z equals, how about this here? Something like that. Let's see if we do X plus Z. Okay, I guess that worked fine. Trying to think about how to break this here.
I think you can try 2.0 plus 3.0. You will get a weird number.
2.0 plus 3.0?
Oh, no, sorry. Maybe that's not this.
Let's see. I mean, at some point we can kind of see it here, I guess, with 1 divided by 11. Let's see if I actually do Y times 11.0. Let's see if I actually get, I do get 1. But you can kind of see it at the end here. I mean, at some point you just have to say 0.9. Okay, that's going to be, rounded to 1 here. So effectively, I have lost a little bit of precision, wherever this has to cut off. I think that illustrates it well enough here. So, if I, well, maybe I could do like Y times, some really big number here. I guess I'll share a video because I have whatever fraction. Basically, the problem is I can't represent every possible digit, of infinite length with floating point numbers or double precision numbers or anything of that nature, right? So even this 0.333333, right? And I think, really, I mean, I guess that illustrates the problem. If I added up 3 of these, right, do I get, 0.9999, or do I get 1 back? The computer sort of has to make a decision on these things. So that's the issue. So anyway, long story short, when it comes to comparing floating point numbers here, the thing that you typically do if you want to see if a floating point number is 1 is you would do something like, and again, I got to remember my Python here. I've got an absolute value function. Is usually you would say, is 1.0000 minus 1.000, is that less than, some threshold here? And I'm just picking something arbitrary. And if it is, that's close enough, okay, to some number of significant digits, okay? Does that make sense for folks? I'll post another video on Piazza where I've been posting in one of the pin threads. Let me actually just get that started here, just so you know exactly where I'm going to post it. Under the useful things here, I'll post it under week 4 here. So there was nothing useful in week 3 apparently. So sometimes that's how it is. So function inlining. And then let's see. I think I've got an example in C. Again, I don't want to. This week's going to be kind of overwhelming with videos, but just kind of pick and choose. The topics that you're less sure of, or if you do want to go more in depth, there they will be. And I'll try to find an exact example while I wait for any other questions here. I think that's. Oh yeah, go for it.
So is it okay if you can look at the problems I posted on Piazza, the relatively longer one about vector resizing?
Vector resizing. Yes, I can look at that. Let's see here. Let me see if I can find your Piazza post. Vector resize behaviors.
That's the one.
Yeah, let's see. Oh, okay, it's public, so I'll bring it up here.
That is.
Okay, let's see. Each time vector resizes. Okay. In your resource manager, are you storing things in a vector? Is that what's going on?
No, it's I think it is the
just
STL graphics program, the starter code. The whatever the starter code provided us. Here's the M sprites. That's a vector that this is called. Maybe it's better if you look into the Git repository and find the code there.
Okay, sure. Yeah, let me open this here. Let's do that here. Actually, I think I've got it. Let's see here. This is in Sprite, you said?
No, the vector itself is in the STL graphics program.
STL graphics.
HPP. I mean, it is defined the header file, and it is used at the end. I think at the startup function.
Let's see here. Okay.
So yeah, this is what I'm talking about.
Yep. Okay. Let's see, and that's causing problems here.
Yeah. So it looks like because we're using a vector, and vector resizes whenever it goes out of space, right?
Correct.
The objects inside the vector gets destroyed and then recreated, and when that happens, the move constructor nor the copy nor the move constructor were caught, and instead some compiler generated constructor was caught instead, and the file name that I'm storing inside, which function was it? Was it in the STL? Did I? In the sprites, let's see. Let me double check. The file name I'm storing in sprite because I want to keep. I'm using the file name as a key, so I'm storing that in the sprite header file.
Okay.
And that file isn't getting copied, which is causing problems because sometimes my objects are being recreated without file name. That's a problem. To load any files, we cannot load any file with empty file names. And then, so what I did is I changed the move constructor. So currently in the sprite.hpp, we have the move constructor equal default. And when I get rid of that, and then basically move constructor looks almost just like the copy constructor. And then the copy constructor will be called by the vector when the vector resizes, like doubles its size. So that's kind of the problem that I'm running into.
I see. I think the way to mitigate this is, well, there's a couple things we could try here. So I guess this is working fine otherwise, right? Before you did anything, is that true, or?
No. So with the starter code provided, it's whenever, like I said, the vector resizes, and then when that happens, file names sometimes are empty.
Okay, let's see here. I just want to run it and see if it.
Sure.
Let's see. Okay, so it is doing this. I mean, so this must be. Well, it's running. Is that not what you got when you ran before? Let's see. So allocated.
But the copy constructor, the copy and the move constructor were not used during the process, right? So.
Yes. Let's see here.
So the file name that I'm storing in the sprite object are not being copied.
Oh, I see. Okay, so let's do this again in GDB and see if that's.
Good.
Let's see. Start. Okay, let's see, where am I? Okay, so if I just print out and sprites, print and sprites 0. Let's see, and let me actually see here. Now msprites, did I store the name anywhere? Oh, I see, because you're trying to store the name.
Yeah, I'm storing the name so that I can, when I call the destructor, I can find the corresponding texture and surface and freedom when I need to. That's what I'm doing. Yeah.
I see. Yeah, I think if you let's see here. Okay. I'll quit this here. Okay, image file name. Okay, so you did add the, yeah, I think if you add the image file name, and let me see, what did I give you here? Good sprite. Yeah, I guess I did store the file name here, which could have been useful. Let me just think about that. And what did I give you? I gave you default move constructor. Yeah. So I'm able to get away with. This is going to work fine with a default move constructor. Did I implement a copy constructor?
There is a copy constructor, but it's not being called on my end.
I see. Because when you resize, I guess there's a couple ways to do it. I'm just trying to think about this. Yeah, these are the tricky things about C++. One way to simplify this problem, on occasion when the vector, there's a couple ways to solve this. Let me open up the SDL graphics program, or where I would start kind of looking to solve this problem. Emplace. So this function here, the emplace back, is trying to basically construct the object in place to avoid the copy constructor from being called. That's the sort of purpose of it, to move construct it and avoid a copy. You could just use pushback, which is fine, which I think pushback will do the right thing if there is a move constructor. I've got to check. In C++, again, meaning that it's pretty efficient, right? Because you'll notice I'm not, the other way to do this, and maybe this is the easiest way to do it, right, is just to create a sprite, temp sprite, put the arguments here, and then you would just say, temp sprite, don't mess with this, just say, push back here like this, okay? That would be fine. And then when you keep pushing back sprites into the vector, eventually it has to resize to make more room, right, as this data structure grows. But if I know, and again, these are little like micro optimization things I'm trying to balance, showing you or not showing you. We probably want to do something like msprites, because I know exactly that there's 50 here, so why not just reserve? Try playing around with this a little bit and see if you run into the same problem.
So I've tried that already, so that will work. So that I have confirmed that this is working. Nothing wrong will happen if I reserve enough space because it doesn't resize.
Sure.
And I think I've also tried pushback, but it doesn't really work the way that I want it to. So do you mind if you try to remove the move constructor and see if the copy constructor is called? Like just comment it out in the header file. I think because we don't have a body just yet.
Sure. Yeah. Let me see here.
Yeah, you might wanna have the.
Let's do this. Let's see here.
You might want to go back on the temp sprite thing.
Here?
Because it's not, because it's not in fact it's not creating the right sprite, right?
Let's see. Yeah, I might have to do all this stuff. Yeah. Okay, let's see. What is this thing here? Okay, yeah. Here.
Yeah, that should work, I think.
Should work. Okay. Let me do a few experiments here, I guess.
Okay.
Assignment 3. Okay, let's see. So this works here.
A copy code. Oh, okay. So the copy is in code.
Okay,
here
it
it
is.
is. Yeah, then it's code. But before that, it wasn't code. So that's kind of my one of my questions. My Piazza is like why is the move constructor called first when it's default, and then when I change it to not default, when I implement it myself, the copy constructor is still called over the move constructor. Those are confused.
That is kind of confusing. Let's see if if I reserve now, then let's see if that avoids copies.
That I think that should avoid using copy. Yeah.
Let's see here. Yeah. Okay, that's good.
Mm-hmm.
So we like that. And then let's see if I do pushback here without the reserve. Let's see here. Oh, let's see. What did I do here? Oh, pushback. Now I have to create this thing here. Sprite, yeah, something like that. And sprites. Something like this. Okay. Let's try to recompile that. Let's see, it's gonna make copies. Yes, almost every time, right?
Okay.
We're passing it in.
Okay. But does your copy constructor will your copy get called if the move is there? The move constructor is set to default. Can you try that? Like uncomment out the line. That okay? Yeah, that.
Yep.
That did I try that? I don't think so. Let's see.
Let's see here. Okay, so it's building. And then just for our record, so we've got the move constructor default.
Then we have
and then pushback, no reserve. So let's see. The question is, let me just try to formulate the question here. Can this move constructor be used so that when we push back, I think since there's still no memory, so at the end of the day, we do have to copy the current contents of whatever is in the vector. I don't know if we can just reserve and then move. That would be the ideal thing, right? Every time we push back, we would just want to say double our size, right? Reserve, and then move everything to avoid the copy constructor. Now let's see if it does what we want here. Now this looks like it is just calling.
Good.
Now I wonder if we actually implement the move constructor without the default. Let's just kind of do this lazily.
Yeah, I mean, yeah, it's I think the same as copy constructor.
Yeah, it should be. Yeah, let's see here. Yeah, because as long as we're not allocating any memory, or I guess with our pointers, let's see here.